We have Zach, who is going to be presenting to us about implementing distributed tracing. Zach's a senior engineer at Numerator, where he works on machine learning operations for a deep learning team. He's from down in Oregon, where he likes to go. He likes cooking, hiking, and playing video games. Welcome up, Zach.
Cool. So I'm Zach, pronouns he, him, his, and I'm here to talk about distributed tracing. If at any point you're having trouble reading or following along with the slides, there's a link right there at the bottom to take you to this presentation. That's actually like how I'm presenting it right now. And if you have any questions, feel free to talk to me afterwards. But let's get started. So I've got like a detailed roadmap here of what I'm going to cover in this talk. I'm not going to read it line by line right now, but general idea is I'm going to be shifting between concepts and examples for distributed tracing. So we're going to talk a little bit about concepts, go to some examples, concepts, some examples, and of course, show some actual Python code. But let's give a very high-level overview to start off. Distributed tracing, hereafter I'm going to be referring to it as tracing. That can get a little confusing, but distributed tracing follows requests through a distributed system. It's an observability tool for distributed systems. So think like microservices. You're actually following an individual request from the time it enters your system to the time it leaves. Let's motivate how this works and the vocabulary for tracing with a quick metaphor. So I think a useful metaphor here is commuting. It's something we all have done, used to do, maybe we still do. You have a trip, you are a person traveling through a system, and that system is transit. So your trip has different components, different legs. So you might be walking for a little bit, taking a bus to a train, walking a little bit more. These separate components, taken together, comprise your total commute. This maps onto the terms in distributed tracing of the trace and the spans. Each one of these little legs would be a span. Your entire trip through the system would be the trace. You want to record information about the different parts of your journey. So one thing I was implying with this diagram is you want to record the type of transportation. Say it was a train or a bus by foot. But in practice, when you're doing tracing, you want to record a bunch of information that's not necessarily present across all of your different spans. So for example, you might want to record the type of train or the type of bus taking you between place to place. Now, if you're not on a bus, you're not going to have a bus type. In practice, you prefer to do this because you really want as much information as you can. So this is a schemaless data system. And to be a little more specific, you are recording a bunch of information. And basically, I'm trying to motivate that traditionally, when you're doing distributed tracing, your backend isn't a SQL compatible data storage. You tend to prefer something with high-dimensional sparse data like a document database or a log stream. So this is kind of a useful metaphor for us, right? We're one person going through a commute, but when you're an engineer tracing a system, you're not actually going through the system. So instead of imagining yourself commuting, imagine yourself as some kind of urban planner or city planner. You're not just looking at one commute now. You're looking at hundreds of thousands, millions of commutes. If you had all this information, how long did different spans of the journey take for people? You could begin to answer really complicated, in-depth questions like, of people who are late to work on a particular day, what route did they take? You could begin to actually look into causal inference of what caused there to be so much more traffic on this one particular street on this particular Tuesday as opposed to an average Tuesday. And you can answer questions like, how does a delay in one system affect a delay in the whole? Is it, 1-to-1, a minute added on the bus line adds a minute on the train line, or is it, exponential or some other different linear effect? This is where distributed tracing comes in handy. So there's the metaphor. Let's talk actual concepts. By now, probably have gleaned that traces follow a request through a system, like a person through a commute. Spans make up traces. Each trace has at least one span. Having a trace with just one span would be a little boring, so in practice, it's often many spans that make up a trace. We assign tags or attributes to those spans to record information like what type of transit, what type of server, that sort of thing. And the tags don't have set schemas. You're not limited to things that would be universal across your spans. You want to record as much information as you can. Before I go any further, I want to make a note that tracing is an open standard. So I'm going to focus on some particular technologies, but this is really a narrowed-in view. It isn't the whole view of the system. A lot of systems can implement distributed tracing and follow these standards. Open source systems as well as proprietary software can follow these standards. I'm going to focus on the open source side. I'll be looking at the OpenTelemetry client. It used to be called Open Tracing and Open Census. And for the backend, I'll be looking at Jaeger, which is a very common tracing backend. And with that, we're ready to talk about an example system. So I wanted to talk about a software problem that we all might be familiar with, we all might have come across before. So I'm going to talk about FizzBuzz. If you don't know, it's a pretty simple problem. Given some integer, if the integer is divisible by 3, have your program return fizz, 5 buzz, 15 FizzBuzz. It's just kind of a fun little exercise to check that you know the modulo operation. And we're going to solve this problem today. But because it's 2023, we're going to solve this with microservices. So I've got FizzBuzz as a service. You can actually check this out now. If you're interested in investing, please talk to me after. And I have a little demo available. I'm going to be referring to some demo code. This is the link to that code. I have a demo repo up where all this stuff lives. So if you want to run this stuff on your own or see the code, you're more than welcome to check it out. I actually encourage it. A quick little architecture diagram. We'll have some client connect to one hub service, send JSON payload to that service. That service connects to 2 separate services, a fizzer service and a buzzer service, gets those results back, then gets the actual response that we want, returns it to the client. And I'm going to show a quick demo, but I just want to explain what the demo is doing. So I'm going to show a bash for loop to FizzBuzz the numbers 1 through 15. We're going to send that to localhost 6000 where the hub service is exposed, and we're going to encode the number in a JSON payload where the key is just number. All right, and here's the demo. And it's starting to run, and you can see there 3 got fizzed, 5 got buzzed, and we get to 15, we have FizzBuzz. So it's working, it's live, we have FizzBuzz as a service, but it seems like it's a little slow. So we're going to trace it. I probably saw this one coming. I have a PR open for this if you want to see what the code looks like. It's also available at the branch tracing example. To run that with Docker, you can run Docker compose profile tracing up, and it'll run the tracing services as well as Jaeger. We're still exposing that hub service at localhost 6000. We're also going to be exposing the Jaeger UI at 16686. This is convention in Jaeger. In practice, you can map this to whatever you want. Okay, so we send some requests through again, and now we can actually look at our traces. Here's what tracing looks like, and I want to clarify, I probably should have covered this sooner. These are Python servers. So I haven't shown Python code, haven't talked about Python code, but to motivate this, yes, these are Python servers, Fast API, and Flask web servers. We can actually check how long things are taking in this system. Let's look at Jaeger. So when you pull up localhost at that fancy number, you get this UI, and it shows you the services that you have traced. And in practice, you just choose whatever you're interested from this drop down, and you click this Find Traces button at the bottom. This takes you to a view that looks like this. We have kind of a graph and a table here. The graph shows you the distribution of your traces. Y-axis is how long they took. X-axis is when they actually occurred in time. And then we see for each trace, all the spans collected for that trace in the rows of this table down here. If we click into one of these rows, we get a view that looks like this. This is what's called the trace view, and it's super helpful for identifying bottlenecks. So this shows 6 separate spans we have collected into one trace. We can see 4 spans for that hub service, and we have 1 span for the fizzer service, 1 span for the buzzer service. The important thing to get from this diagram is this fizzer service is taking a really long time. It's actually a little bit cut off here, but it's taking like exactly 500 milliseconds more than the buzzer service, almost like there's a sleep 0.5 somewhere in the code. But this is actually how you identify bottlenecks with tracing. This gets you pretty far in the process. Let's talk about how this works, though. And when I was approaching this question, how does tracing work, I wanted to cover it in 2 different ways. One is, what is the actual process by which we do tracing? And then one is, how do you do this in Python? Let's start with the first one. So tracing works by operating on what's called context, or trace context. The context just indicates what the trace, the current trace and the current span is. So there's a quick little flow chart I have. Your program's going to check for context. If it finds context, it knows to start a span associated with the trace that already exists. If it doesn't find context, it has to create a trace and a span at the same time. And how we communicate this between our servers is we propagate it through HTTP headers. So in practice, this isn't the full specification, but in practice, your headers will look like this. You'll have a trace parent header that includes both the trace ID and the span ID. And this is enough information for your server to reconstruct, okay, I know this particular request is doing this thing, and I can add a span to that request, and we can get that nice visualization back in Jaeger. There's a full set of standards for this, though, much more in depth than what I'm showing, so please check that out if you have questions. So again, high level, let's take a step back. A program is going to create a span associated with a trace. Our tracing client library, in this case OpenTelemetry, sends the span to the backend, in this case Jaeger, and the backend server accepts and stores the span, and a front end for the backend, so in this case the Jaeger UI, lets us visualize those traces. That's kind of the process. What does it look like in Python? It took me a while, but we're finally here. I'm going to be talking about some Python code. OpenTelemetry is a really fun library to work with. It has a rich collection of packages, a whole bunch of them, and even it has something called auto-instrumentation to make this really simple to get started with. I'm going to be showing examples for Fast API and Flask. There are a bunch of other examples as well. And I'm going to be looking at diffs to emphasize what tracing does. A little faux pas on my end, these do include red and green diffs, but so if you're colorblind, it might be a little hard to tell apart, but I can get that updated later. And the important part is the plus and minus will also indicate what changed. So the first thing you have to do when you're setting up tracing with Jaeger, you have to configure your exporter. This is a whole bunch of code, and I kind of just wanted to throw it all at you because it is a whole bunch of code. There's really no way around it. But the general idea is we have to tell this OpenTelemetry client that we're sending stuff to Jaeger. So we have to actually encode the name of the service, how we reach Jaeger, that sort of thing. And then there's kind of a bunch of magic functions that take you from point A to point B. Once we're there, we can start tracing our services. So this is what an untraced hub service looks like. I've just got some requests. I've got one function here that's calling one of those other services in case fizzer or buzzer, and it's using just request.post. That's it. So when you're posting to that hub service, it gets the number out, and then it does a fizz and it does a buzz remotely. When we add tracing to this, this is with fast API auto instrumentation, it's going to look like this. So the important things are we have to propagate those headers, that trace parent header I was talking about before. We do that with this inject function. We inject the headers, and that takes a headers dictionary and in place adds the trace parent header and some other information that makes it so that the other services can consume the trace by setting up their context. Then we just add this fast API instrumenter, and we're ready to roll. This sets up tracing. The story for auto-instrumenting Flask is pretty similar. So here's what one of those fizzer or buzzer services look like. They're both Flask services. Probably about exactly what you'd expect. Takes the JSON, reads the number, does the modulo, returns the result. And the big difference here, this is pretty similar to auto-instrumenting Fast API, but the big difference I found here is I moved away from JSONify, a Flask function, to make response, because again, we have to manually propagate those headers. I also wanted to show a quick example of manually setting up tracing. This can be useful for when you're working in an environment that's more specific than just one route in a web service, or if you're working in a sub-process, something like that. So this comes up more often than you'd think. So here's the fizzer service where I'm actually going to do a manual trace. Looks very similar, pretty simple. Here's what manual tracing looks like. So I import a bunch more stuff. There's a bunch more added in the diff. And it feels a little more magic to me. So first thing we have to do differently, we actually have to get that trace parent header ourselves from the incoming headers. Then we have to do this trace context text map propagator dot extract, which took me forever to find. So I'm very happy to share it with you all. That's how you get the context into the program. You start the span with that context here, this with tracer as current span, start as current span. And then it's the same as before. We're taking that, we're injecting those headers to add the trace parent to the upstream server so that we can keep tracing the request. One more note on the difference between manual and auto instrumentation. Auto instrumentation adds a bunch of tags for you based on the incoming requests. So this is pretty small. You might not be able to see it, but it's things like the HTTP scheme, the HTTP host, the method. A lot of this stuff is getting added for you automatically. When you're doing a manual instrumentation, though, you don't get many of those things. So here's a quick example of what it looks like. You basically take the request, parse the header, grab it yourself, same thing as before, then you use this set attribute to set one of the tags. So if you want to add custom tags, you use set attribute on the span, and it's going to show up in your visualization later. Cool, Python's over. So let's talk about results. Tracing's clearly a complicated solution. Unlike, say, logging or other forms of observability, it requires some pretty substantial application code changes. And this often gets brought up, and it's kind of like the end of the conversation. I think it's really the start of the conversation because, yes, tracing is a complicated solution, but we're in a complicated problem space. We're trying to understand how requests flow through a huge distributed system. That's not an easy question to answer. Lessons from doing this on my team. So some particular experience I have with it. We found a large bottleneck in one of our services. with auto instrumentation, so just low-hanging fruit. We created some manual spans and identified some slowdowns in third-party softwares that we're using. We're able to rectify that. And one thing I did want to note is that it's really easy to configure sampling. In practice, you're not tracing every single request. You're tracing something like 1 every 10,000th request. That's configurable with environment variables, which is super nice, no code change needed. You can just tweak it on the fly. Some negatives from doing this on my team. Basically, it's not a core part of our observability in practice. And I think we don't fully have the tools that we need to make it part of our observability practice. What does that mean? What do I mean by that? I'm going to get to that in 1 second. There's some alternatives to tracing. There's a great example, a great blog post here by the authors of Linkerd, one of the authors of Linkerd, how service meshes can get you some of the functionality of distributed tracing. And there's some really encouraging research work being done by some of the people working on Envoy to approximate distributed traces without propagating headers, just based on timestamps of when a request is sent and received in your system. Seems really hard, like way harder than propagating headers, but very cool because this would mean we don't have to change the code. How do you get more value from tracing? Like, what could I do differently? The biggest suggestion I have is to go beyond the trace view, just that one look at the Gantt chart of how the traces propagate, to do a little bit more. So some examples of what that can look like. Services can actually operate on traces. You can be parsing that trace parent header and doing things with it programmatically, like demarcating types of traffic. And you can analyze this to analyze your traffic patterns live, which would be a really powerful tool. There's a great post written by Dan Liu here about how to build tools on top of traces. And one of the key ideas he has is to back up your traces to a SQL storage. Drop a lot of those high cardinality keys, just keep some basic stuff, and your developers can use what the tools they know to build some custom dashboards. And if you are thinking about tracing, I think the best advice I have for you is to read Sydney Sridharan's wonderful blog post on tracing. Her idea, going beyond the trace view is kind of her big idea, but the key idea I would say is to think about it at the service level, not the trace level. Go back to my metaphor from the beginning. We want to be traffic planners or urban planners thinking about what causes congestion, where does congestion come from, and not let's look at 10,000 people going through our systems. So in summary, because tracing follows requests through your system definitively one at a time, it can allow you to answer questions that other tools can't. That said, implementing distributed tracing can require substantial application code changes, and that can be kind of a barrier to entry. I'm hoping that providing some examples today can help lower that barrier to entry to people in the Python world. And finally, I'd say that to get the most value from tracing, I would have a plan in place when you're considering implementing it to create or deploy tools to move your team beyond the trace view. Think about how to use traces as a tool in your tool chest for doing like complex causal analysis of when something happens downstream, what caused it, when congestion happens downstream, what caused it upstream. And that's my talk. Thank you very much.